So for today, we will talk about a new topic. And in our previous lectures, right, we finished talking about bootstrap. So this is a book I recommended in my syllabus. It is actually a book called Elements of Large Sample Theory by Eric Lehman. And I can share the PDF version of this book on our Learn, so you can take it further after class reading. So specifically, I want to use some of the materials in this book to cover the things we haven't talked about before. So as I said, in this year, I want to cover more topics than before. So first of all, this statistical functional is a generalization or abstraction of estimation, non-parametric estimation specifically. In our previous classes, we talked about that. So why do we say non-parametric estimation? The key thing here is we are trying to use this called Fn hat, empirical CDF, to plug in our F. Okay, that's the thing. And any parameters of our interest are expressed as HF. So in this book, you used H to mean a functional, as F is a distribution function, right? CDF function. So H is a functional applied to this distribution, and we call that as our parameter of interest. So the idea is, as long as we can have an empirical CDF to estimate F, then we can just plug in this Fn hat to replace F to get our estimator. So essentially, the estimator we want to get is H Fn hat. Okay, this is the general idea. And it's called non-parametric estimation because this empirical CDF written in this way, for a specific value x, we just calculate the proportion of our sample less or equal than this value x. This is called non-parametric, right? We're not making any parametric assumption about f. That's it. So essentially, you can think about the statistical functional as a general way to do non-parametric estimation. Our hope is that Fn hat is a good enough estimator for f, then plugging it into the functional, we have a good estimator for this parameter. Okay, so that's the general idea. So I will skip the details in this book, but I'll just quickly show you. It's a very basic review. Essentially, I said this, we're going to use this HFN hat to estimate HF. And if our HF in the simplest example is just the mean parameter of F, we can write that in this way: expectation under F of a random variable X from F, right? This is our mean parameter, essentially. So to estimate this mean by plugging in, what is expectation? What is the HFN hat? It's actually by plugging expectation under Fn hat of a random variable, I just call it X star from this Fn hat. Okay, just try to distinguish the two. X is from F, X star from Fn hat. So when we say X star from Fn hat, what do we mean? We mean that X star follows a discrete distribution specified by Fn hat. Essentially, Fn hat put point mass 1 over n at every value, every dot, every data point in your sample. So that's why under this discrete distribution, this is exactly the expectation you will get, right? And that is the sample mean. So basically, you see in this plugin, simplest plugin case, sample mean is an estimator of population mean. So we are basically talking about the simple fact we learned in our introductory statistics in this statistical functional setting. Okay, second example, when this parameter is what? Is actually the kth population moment, okay, centered moment. We're taking random variable x following f, subtracting its mean, taking the difference raised to power k, and then take the expectation. All right, so this is the kth centered moment. To estimate this parameter, then we do plug in. Again, now this whole expectation will be evaluated under f and hat. Don't forget that here, this expectation should be expectation under f. So this f will also be changed to f and hat. So that's why you are putting probability mass 1 over n at each data point in your sample. And this is the expectation under f n hat, x bar, and you're doing this expectation. And essentially, this is the sample moment, right? So again, you see that for those moment estimation, sample moment is just a plug-in estimator for the population moment. Okay. A third example, I'm just doing the quick review using the contents in this book, but we have covered this briefly before, is this one, quantile. The pth quantile is our parameter estimate, right? Then how do we do that? Essentially, if you are doing plug-in again, then you are basically going to evaluate, change this F inverse. You have a way to define F inverse. Remember, we talked about that before. We said the inverse definition depends on the continuity of F. When it's continuous at this P, when it's continuous, then it's easy. You just take the inverse. When it's not continuous, there are some specific specifications we use to define the inverse. All right, so this is the plugin version. So the natural thing is to change F to this F n hat inverse. But something is missing here. It's even though it's a book, but this is P. P is missing here. Okay. So what do we do? For P equals 1/2, then this is actually the median. Population median, sample median. Okay, but here we're talking about specific case where you have median, but essentially your sample size is even. Okay, when it's even, there's no single value in your x1 to xn that can be picked as the median. Remember that, right? Because you have two things in the middle. So essentially, it says that this can be defined any point in this interval, right? So basically, we divide m by 2, we call that m. It can be anywhere between xm and xm plus 1. They are both the median. Okay, but as we defined this inverse in our previous lecture, we defined to be the minimum, right? Lower bound of this interval, and that is xm. Okay. On the other hand, you see this is the plugin version. Plugin version estimator for the population median is this xm. But the standard definition in the sample median is the midpoint. We take these two possible data points that can both be median, we take their average. Okay, so you see, this is the plugin. This is standard way, the one you do intuitively. But you can imagine, right? If your sample size is large enough, then it doesn't really matter because the two values xm and xm plus 1 must be very close to each other, right? That's why it's asymptotically equivalent. Okay, so, and another thing which is used in this book, I think it's just good to know as a notation because you may see it somewhere. So when we say that we do the expectation of AX with X following F, we can actually use this integral notation. That is, we take the integration of A as small x, and the small x is sampled from the distribution F. So basically, this dfx just refers to the density, right? So basically, you can write it in the equivalent way, ax, fx, dx. So essentially, fx is the density correspond to the big fx. This is the CDF, this is a CDF, and this is the PDF. Okay. And this is a general notation because essentially, we use this notation here in this book to also include the discrete case. Because the way I write here is only for continuous case, right? But this is a notation that can include discrete case. Yeah, that's it. So essentially, having this discrete case included using this notation, ADF, why is it advantageous? So basically, ADF is by ignoring the small x for simplicity. It is advantageous because it includes the discrete case so that when we talk about plugin and the empirical CDF is discrete, it can be directly used. Okay, so so the plugin will actually work for this notation as well, right? So this is for the discrete case, and then the true CDF may be continuous. Okay. So multiple integral can be extended. I'm just going to ignore that part. Now let's look at some of the goodness of fit statistic. Okay, this is an interesting topic. For testing the hypothesis H that the distribution F equals some specified distribution F0. Okay, so we're trying to test this hypothesis. So typically we write null hypothesis as H0. In this case, we just write F equals F0, okay? And we have a sample. The sample is an IID sample from F. Okay, that's the setup. And how can we, what test statistic can we use? So there are a few. The first one is the Kolmogorov statistics. So this one is something you have seen before. Remember the Kolmogorov-Smirnov theorem, right? So in that case, you actually have the uniform convergence of this. Remember that result is about sup x f n hat x minus fx converge to 0 almost surely. That's the thing we had before. It's a very, very strong result to justify that empirical CDF is good, right? Yeah, so we have this result, put it aside, and now we're using this to define a statistic. So essentially F0 is the distribution with a known form we specify in our null hypothesis. We specify that f and x is based on our sample, x1 to xn, putting 1 over m probability mass at each of them, and we take the difference and take the sup. Okay, this is the Kolmogorov statistic. The second one is called Kramer-von Mises statistics. So you see, what's the difference? Here, you're not taking the sup, but you're taking the square difference integration. Okay, so you're integrating over all possible values of x by assuming x follows f0 under the null. This is the integral one, so more like an average, right? So essentially, this can be written in what case? This can actually be written as the expectation of f0 of the square fn x minus f0 x is this expectation, right? X follows f0. Okay. The third one is the classical Pearson statistic. Okay, what is this? So essentially, Pearson statistic always take this formula. If you don't know it, it's always the summation over all possible values of the observed probability minus expected probability square over expected probability. It's always in this form. Okay, so here the Pearson statistic is specified by discretizing. Actually, we're doing this discretizing of the null F0, right? So Fj0, so we have J go from 0 to R. Essentially, we are dividing the domain of my random variable here into R plus 1 intervals. Okay, we're calculating the expected probability of this interval ij under the null f0, and this pj hat is the observed proportion of your data, of your sample observations in this interval. And you can see this Pearson is a discretization because this R needs to be specified. It's how much resolution you want to have for this discretization. So each of the statistic, all right, is of the form HFN hat. Because what? Because you use F and hat, right? This is F and hat, this is F and hat, and this PJ hat is also based on F and hat, based on your empirical CDF. Okay, so then you can find the corresponding H functional. For the first case, it's just the sup, right? And it missed the X here. It's the sup X of fx minus f0x. Here you are using f and x, and it's plugging f, so I'm just replacing this by f, and I get the functional on f. Second one is this integration. It's obvious. How about the third one? The third one is also can be expressed in terms of f. If in terms of f, I just express what I previously, you see previously on that slide, this is written as PJ hat, right? Based on my data. I just change it to PJ. And PJ will be what? PJ will be the probability I have in this interval from AJ to AJ plus 1 under F. That's it. So everything can be expressed as a statistical functional. Okay. All right. So estimating a CDF is this example, right? So we know that empirical CDF is just this thing, number proportion of your sample under this value, right, among your n data points. This is just the usual estimator of the unknown probability of an event by the observed frequency of its occurrence. Okay, however, how do we study the behavior of this empirical CDF? It's actually following binomial distribution. Essentially, if we define the fact that a random variable under F, the probability of it under A, if we denote this to be FA, the true CDF function, then essentially for my sample of size n, each random variable in my sample follows a Bernoulli, right? For the Bernoulli to be under A or larger than A. So together, the number of my random variables in the sample that are under A follows a binomial distribution, right? So basically we denote this to be Y over M. So this is a notation. Y denotes the number. So Y itself follows binomial, where the binomial probability under A is FA. Then for sure, we know that expectation is P, is this P, and variance is P times 1 minus P. Here we call it Q over N. So these are just standard binomial result. Then, because F and A is just defined as Y over N, then we can easily see its expectation is FA and its variance is this. So clearly, this empirical CDF at A is unbiased. Most importantly, look at its variance. The variance is in the order of 1 over M. Okay, essentially, what is that? The variance is on the order of 1 over M. We can apply central limit theorem, okay, by just multiplying the difference between empirical CDF at A and the population CDF, true CDF at A. Taking their difference, scale it by root n. Essentially, the variance of this term will have nothing to do with n. It stabilizes in the asymptotic variance because the 1 over n will be canceled by this n, right? Because variance will put square root of n outside to be n, square it. That's how we get this. So essentially, we have a very nice result for this empirical CDF, that is, it is a consistent estimator for FA for each fixed A. However, a much stronger result, I just said that already, much stronger result can be obtained by this uniform difference, right? Over all possible x's, I take the maximum. Yeah, so, and also I said that this can be even can be even made stronger into almost sure convergence. Okay. All right, so I think I can skip most of it just as a very quick review because we talked about this before, statistical functional, and I want to quickly move on. Okay, so in this book, you can take an after class reading, estimating the mean by plugging in, estimating central moments by plugging in. We already said that, so I'm going to skip this. And this is also a review of our previous classes, U statistic, V statistic. We covered this already, right? V statistic essentially is a direct plugin. Is this the V? And U statistic is just by removing repeats in this hypothetical sample, which are sampled from the original sample with replacement. So U statistic require these eight random variables sampled from my original sample, require them to be distinct. That's it. That's the U statistic, unbiased. Okay. But basically, you can consider U statistic to be a modification. So this is V, right? I consider all enumeration for A things I need in my function to define the parameter, I'm considering n to the power a because each one can be sampled from my sample size of n. While in U, scrolling down, you see I'm doing this. Okay, they're talking about a equals 2. For a equals 2, let's compare these two things. V is enumeration n squared, while U is not. U is n choose 2. Right? We consider all distinct pairs of I and J. So I must be equal to J. But in U, I and J can be equal. That's it. Okay, so, and regarding the asymptotic distribution, we talk about this. And in this book, it tried to derive the asymptotic distribution for V statistic first, okay? And then it shows that asymptotically, V and U follow the same distribution because the repeated terms in V can be removed. Essentially, the unbiasedness for U statistic is only in the finite sample sense, not asymptotic sense. So it's a finite sample correction. Just like in our estimation of sample variance, estimating of variance using sample variance, we can use 1 over n version or 1 over n minus 1 version, right? Asymptotically, they're equivalent, but the 1 minus n minus 1 version is finite sample unbiased. Okay, finally, I think I can move on to say this. Okay, this is something we didn't talk so much about, but I hope to just provide some insights on this. Limiting distributions of statistical functionals. So this is what we showed already. HF and hat converge to HF in probability when H is continuous functional. And I didn't specify the continuity of a functional here in detail, but it's actually quite intuitive, right? In what is a continuous functional. And in our notes and in this book, there's a more rigorous definition. But what I want to say here is for this section in this book, chapter 6, section 3, it's about this behavior. So in general, what can we say about this error? Error scale by root m. Can we have something similar to the central limit theorem, like a normal distribution with a finite asymptotic variance, right? So if we can have such a general result, then whatever plugin estimator we use for an estimator, we can just apply the general result. We don't have to derive the asymptotic distribution for a specific case. However, we know this will not come in for free because what is the typical thing of applying central limit theorem by delta method, if you remember? Delta method can allow us to derive asymptotic normal distributions by transformation, right? So you can use sample mean minus population mean times root n follows normal distribution by central limit theorem. That's the starting point. Then you can show that for some transformations of sample mean minus the same transformation applied to population mean, delta method can also give you asymptotic normality. But to derive that result, remember the proof essentially based on Taylor expansion, right? You're basically getting a linear term here to approximate this difference. And because the linear term doesn't transform the distribution, Gaussian is still Gaussian. That's why, okay? That's what the reason. So here we need to do something like Taylor expansion for a functional to expand this thing. And we need to create it to be something like the difference between the two CDFs, okay? Anyway, so we ignoring the technical detail, but I want to say one thing that's quite interesting to me and it's good to know is here. Taylor expansion requires a derivative, first order derivative of function. How do we define a first order derivative for a functional, right? If you want to derive this, how do we do that? So for this, we can actually go back to our definition of a derivative. Well, how do we define a derivative? It's defined as a limit, if you remember. So basically, it's defined as this. Let me just write it here. So f prime a is defined as the limit as maybe epsilon go to 0 and FA plus epsilon minus FA over epsilon, right? That's how we define the limit, the derivative as a limit. And similarly, if I want to define the derivative of H at F, right? Because we can consider F and hat to be something deviated from F, and we just want to do something like Taylor expansion. And how do we do the derivative? So here the idea, and we call this Hx prime, is because here we're considering this distribution as a perturbation. So just like here, I'm perturbing A by adding epsilon, okay? And here, what I will need is to perturb my F by adding some point mass at X. So essentially, X is just a value. It can take any value of X. I just put a small probability mass epsilon at this point mass. And then the remaining probability 1 minus epsilon is at F. This is what I call F epsilon X. So it is a small perturbation to my distribution. And based on that, essentially, if I define this thing, I'm defining this. So taking this distribution, which is a perturbation, and I want to take the derivative against epsilon and set epsilon to be 0. Then I define this as the functional's derivative at X for my F. So basically X plays a role here depending on where X is located. I can choose any X to put the point mass here. And in the literature, this has a name. It's called influence function. Okay, so what does it mean? It means, okay, has an interest independent of its role here. So it's something which is good to know. It measures the rate at which the functional H changes when F is contaminated by a small probability of obtaining an observation X. And the small probability is epsilon, okay? And thus is the measure of the influence of such contamination. So in other words, this influence function, let's look at it again. It's written in this book as IF H F at X. Okay, so it means that given your F, and given your F is your CDF, true CDF, given your functional H, how much does a particular value of X contaminate this overall functional? Okay, it measures the change, in other words. So maybe for certain X, the influence is bigger than for other X. Okay. While continuity of H indicates whether the value of H at a distribution close to F is close to its value at H. So essentially, this is continuity, right? Continuity means that if I change my input a little bit, I think my output is only also change a little bit, right? It's not changing dramatically. That's the thing. So we hope that when F is just perturbed, contaminated a little bit, H is not, the functional does not change too much. Okay, so the influence function provides a measure of this closeness, in particular, the influence of a small proportion of observation at X which do not belong to F, so-called gross errors. So this is another thing people denote. That is, if you look at all the possible X values, you pick the maximum absolute influence function value. Call that lambda star. And this is called the gross error sensitivity of H at F. So this is the worst case scenario, right? Worst case scenario, how much H is affected. Okay. So essentially, our goal is to answer this question. The conditions, under what condition can we say about this error? So there are 3 things. We hope to accomplish 3 objectives regarding this inflated zero root and inflated error. First, An understanding of why functionals such as the median or V statistics, which seem so far from being sums of independent random variables, have a normal limit, right? They can still have a normal limit because remember, the median is F inverse P. That's the HF, okay? And for the V statistic, it's actually this thing. And HF is equal to expectation under F of some function at x1 to xa. In our previous class, we use xm. So basically, it's a function defined based on an IID sample with size A, right? Using that to define a statistic, and its expectation is our parameter of interest, right? So for variance, we need A equals 2. For mean, we need A equals 1. Yeah, that's the V statistic. So we can understand the behavior of these functionals. And second, if this one does converge in law to normal distribution, we want to know what's the asymptotic variance. That's another thing. That's what we need for the second objective. Third objective, which is most important, simple sufficient conditions for the asymptotic normality. When does this hold, right? Yeah. Okay, so this chapter is all about this. So essentially, we'll study some behavior of this error and see whether asymptotic normality holds. So let me skip the detail of the examples. For example, one thing you may want to look at is the goodness of measure, fit measure. We previously talked about like the Kramer-Von Mises, this one, whether it satisfies that asymptotic normality. But essentially, I will tell you the take-home message for this part is this. Okay, these are the take-home messages. When does the asymptotic normality no longer hold? First, lack of smoothness, and that's about H. That's about the functional. Okay, the functional needs to be smooth. Condition one, and this is regarding the Taylor expansion thing, or actually regarding delta method. Delta method, here maybe we can just talk about delta method for now. Delta method holds under two things. First, you need to have the F differentiable, right? So to have this convergent law to, let me just write it, 0 sigma squared times F prime theta squared. That's the delta method's result, right? You just entered the first derivative at theta and you square it to basically rescale your asymptotic variance. That's just a transformation of the central limit theorem result based on Taylor expansion. But to have the Taylor expansion work, you need to have F differentiable, right? Smooth enough for Taylor expansion to work at theta, at this true value of our interest. Second, this cannot be 0. Because if this is 0, then you will have a 0 asymptotic variance. Means what? Means that just by scaling this error, difference by root n is not enough. It's still going down to 0 too fast. Maybe you need to scale by n. That's something we showed before. And we'll give you one example showing that you need to scale by n, and then you can get a chi-square distribution instead of normal. So these are the things we need to have for delta method. And same thing applies to this functional thing. So same argument applies to this. If you want to study this behavior, you need to have H smooth enough. And if not, then it's not. So one example I can tell you, which this asymptotic normality does not hold, is this common graph distance as your H. So if you define HF as this, then this H is actually not smooth enough, right? I think the reason is because of soup. Whenever you work with something like a soup, taking the extreme, not just average, right? You always have some problem. We know last lecture, bootstrap also failed when you want to estimate a boundary parameter using your extreme order statistic, like maximum. So that's just how to say, just be aware of that. So in this case, we don't have that. So that's the first thing, smoothness about H. Second thing is also here, vanishing derivative. So here, when this derivative vanishes to zero, asymptotic normality does not hold. Same thing here. So here, basically, we need to consider how the derivative of H at a particular value, at X, is problematic. So basically, if we have this shrink to zero, there's also a problem. But I think nowadays, these theoretical justifications can actually be easily verified numerically, right? So what you can do is that you can, for example, if you have a parameter of interest in your mind, you can easily do simulation, right? You can, as long as you can sample from this F, you can increase your sample size, get your F and hat, calculate your plugin estimator, and if for each sample size n, you can do simulation for 1,000 times, then you can get 1,000 values for your plugin estimator. That will give you a distribution, right? You can just show when your sample size is large enough, does the distribution look like normal? It's something you can easily check numerically. But in the old days, without such numerical, right, computer, you have to rely on mathematics. Yeah, so this is another way to make you aware that technology can make a difference. But I will still think if you verify numerically that this asymptotic normality holds, then it's worth the effort to get this derivation for the asymptotic variance. Because once that you have that, then you have a closed form, right? That will make your further computation and p-value calculation, confidence interval calculation all much easier. That's the thing. Okay, so I will conclude this part. And for the remaining of today, I'll talk about a new topic, density estimation. This is something kind of in parallel to the discussion of bootstrap. We can both use the statistical functional argument for both. All right. So what is density estimation? I would say density estimation is probably one of the most widely used non-parametric estimation in practice. For example, if you have a data point, a set of samples, you have a sample, if you one-dimensional, for example, if you want to just plot the density in R, right? You can easily do that, right? Basically histogram is a form of density. You can also have the kernel density, smooth curve. So these are the things we use for exploring our data to see where the data is mostly concentrated on the mode. Okay, so when the true CDF is continuous, has a density small f, then the small f provides a visually more informative representation of the distribution, right? Because density, you can see where the mode is. But the CDF function changes from 0 to 1, it's not so easy to visualize. Okay, we begin with the estimation of Fy with the given value of y. So we fix the y and want to estimate this Fy. Suppose that f is continuous in a neighborhood of y and Fy is positive. Okay, these are the conditions we have. Continuity assures that Fy is completely determined by f. Okay, you can take derivative at y, and that's Fy. Hence that Fy is a functional, right? Because it's a derivative of f. So that's why functional is a very broad sense. It's like an operator, right? You can take derivative. Define over the class, we use usually when we say a class, we use this calligraphy, right? Math cal for all distributions f with density f, continuous in neighborhood y. Okay. To estimate this functional, essentially Fy equals to HF. To estimate this HF on the basis of a sample x1 to xm from f, we cannot directly use HF and hat. Why is that? Because the f and hat is not continuous, right? Empirical CDF is not continuous. What it is, it's actually a step function, right? It's discontinuous at every value. Remember, For empirical CDF, let's just draw this. Suppose that I have just two values, x1, x2, okay? So what is the empirical CDF? Essentially, x1 takes probability mass 1/2, x2 takes probability mass 1/2. So when it's less or equal than when it's less than x1, the density, or sorry, I should say the CDF function stay at 0, right? But once it reaches x1, it will all of a sudden become 1/2 and stay here. So basically, I have empty here, it jumps to 1/2. Again, I have empty here. Once it reaches x2, it jumps to 1, right? So it's this kind of step function. It's discontinuous at the values in my sample, x1, x2. So that's why such a function, this is my fn hat. This one does not have a density, right? So fn does not have a density, so therefore this just by direct plug-in is not defined. However, what we can see is that we go back to the definition of the density or the derivative. Again, go back to the definition of the derivative. Density or derivative, so this is the definition of df at y dy, right? This derivative is defined as the limit of f at y plus h minus f at y minus h, their difference over divided by the difference of the two inputs, 2h. Definition of the derivative. So with this, then for this one, we can do plug-in, right? We can easily do plug-in by this. We compare the two. So this is the plug-in version. We call it fn hat at y. So we are just changing f to fn hat in both terms. That's it, nothing much. Okay, and how does this behave? Because we know for n large enough, fn hat goes to f in probability, right, for each term. So therefore, their difference and this ratio will also go to this in probability. So essentially, we know that the latter, this will converge to that. But of course, here, in this case, you're having h go down to 0. So h must be small. So essentially, we already have this estimator. This estimator at y is calculated by just counting my samples, my sample in this interval between y minus h to y plus h. Divide that by the bandwidth. H is called bandwidth. Yeah. That's it. Okay, so I should say it's the sample, not the sample, but proportion. Proportion of my sample in this interval divided by 2h. And this thing is called this naive density estimator. It's called naive density estimator. It is a consistent estimator of Fy, as I said. For suitable sequences h0n. So basically, as you want this h to go down to 0, h must be small. You can specify h to be a sequence of n. So as n goes large, h can go down. This also makes sense because when your sample size is large, you can afford this h to be small because no matter how small the interval is between y minus h to y plus h, you will have some sample in there, right? So you can have an estimate of the proportion. Okay, but it is interesting to know that Fn, this thing, estimator, is itself a probability density. It is non-negative, and we can easily show that it integrates to 1 across the y. Yeah, this can be shown. The reason is because when we do such an integration, we are going to leverage the fact that, let me see. We can actually leverage the fact that using this interval going down here, So essentially, I'm rewriting this based on the interval. The interval is just counting how many of my points lie in this interval, nothing much. So I go through my x1 to xn and see whether each xi is in this interval. Okay, and then using this form, you do the integration, you just do the integration. And then you are going to basically take this integral using the indicator function because it's only about the interval xj minus h, xj plus h. And then you can show that integrates to 1. Yeah, because the interval is specified to be 2h long. Yeah, and that 2h and this can be canceled. So essentially it's just the way you express this empirical naive density estimator. Okay, and for this naive estimator, we can also easily study its property, like the bias and the variance. So the bias is clearly this, because your interval is length 2h, right? And in this interval, your expected proportion of data points should be based on the true CDF. Right? True CDF applied to the two ends of an interval, take the difference. That's P. Because you know that P is specified to be this. This is the definition. You define P to be this, and this is the expectation. So P over 2H. So therefore, the bias is this P over 2H minus Fy. Right? So, but if you know that by taking H to be small, let H go to 0, take the limit, that's exactly Fy. Right? So you see this bias is going down to 0 as long as H is going down to 0. Right? The reason is just what I said. Fy is just the limit. That's it. Yep. So which tends to 0 provides that H go down to 0. So this is the first condition we need to pay attention to. To have the density estimator good, the bandwidth need to go down to 0. The reason is because the density is defined as the derivative. Variance. Again, the variance can be derived based on the binomial property, right? In the interval versus out the interval, how many in the interval, that's a binomial counting thing. So this is the variance. And for this one, let's look at this. So given this variance, if we specify this difference in the interval or the probability in the interval as Pn, so it's just that we are given the sequence n to make sure Hn go down to 0 so that the corresponding P becomes Pn and it go down to 0. The interval length is going down to 0. So then we put this P n here. What do we have? We're just trying to separate the two things. So 1 minus P will go to 1. So we put it as 1. And we are just left with Pn. Pn itself will go down to 0. And we have this Pn over 1 copy of Hn here, and the other copy of Hn here. So this rewriting has some benefit because for this part, this is what? This is actually having a limit as my density, right? Remember the density Fy is defined again as the limit of Fy plus Hn minus Fy minus Hn 2 over Hn, right? And this, and as n goes to infinity, and this is exactly Pn, what I call Pn 2Hn. So that's why for the first term, we have a limit as Fy. We know it's positive. That's why we need this positive thing. Remember the condition for estimating. If it's not positive, you won't even have any sample there, right, to allow you to do the estimation. Okay, if you want the variance to go down to 0, you just need the second term to go down to 0, because the first term is going to Fy. The first term is converging to Fy. You just need the second term to go down to 0, and that is equivalent to having the denominator in the second term to go to infinity. Okay, so that's the second condition. We have two conditions. One is hn go down to 0. Second, n times hn go to infinity. So in other words, yes, you want your bandwidth to decrease as your n increases, but it cannot decrease too fast. It has to be decreased at least slower than n, than 1 over n, so that their product is still going to infinity. Yeah, I think this is the intuition underlying this. So yeah, this is what I said. That is, if hn tends to 0 more slowly than 1 over n, or hn, yes, is smaller than 1 over n. Or it's bigger. 1 over n is smaller than hn. Hn is going down to 0 more slowly than 1 over n. Yeah. But this is a weird way to write it anyway. So basically, we'll just say that the two conditions, let me just repeat again. So the theoretical results, theory, a sufficient condition for the naive density estimator to be consistent estimator for Hy is for both these two concepts to hold. I'm just rewrite it. Hn go to 0, and the second is n times hn go to infinity. You need both. Yeah. So one thing I don't really like about this book, I think just one minor drawback, is that a lot of the references to the equations, the numbers, you have to go back to find it. But I think for simple things, maybe it's easier to just write it out, right? Yeah, that's what I think. Yeah, if I'm going to write a book. Okay. Okay, so another thing we modify for density estimator, which is also very important. Let me just read this paragraph. So it's a justification for further development. Although f and y is consistent for estimating fy when the h satisfy these two conditions, right? I just wrote. Note that f and y as an estimator of fy involves two approximations. First, approximating this derivative by this ratio. Second, approximating this ratio by plugging in f and hat. So two approximation. Yeah, we have two approximations here. As a result, the estimator turns out to be less accurate than the one might have hoped. However, before analyzing the accuracy of f and hat y, let us note another drawback, which is what? The estimator f and hat y, although a density, is a step function with discontinuities at every point x plus minus h, right? Remember that we are doing the proportion calculation by only counting the sample, the observations in this interval. So essentially, if an observation is in the interval, it will be used to calculate the proportion. But anything right after outside of the interval will be discarded. So there's no smoothness in our sample usage. That's the problem. So if we assume the true f to be a smooth density, we may prefer its estimator also be smooth, right? So we want to be more smooth. To see how to modify this f and hat for this purpose, consider the following description. Okay, 6.4.2. Let's look at it. It's this one. This one. So this is the naive estimator. Naive, we want to modify this. Okay. So right now it's just using this interval, like I said. So essentially, it's like if you give every point a weight, you are basically say, okay, this is my y, I minus h, y plus h. So the step function is like this. If you're in the interval, you are counted. If you're not, then you're not counted, right? That's the thing. So for every sample, it's the weight of entering this calculation. It's either 1 over n here, or it's 0 here. That's the way it's calculated. but we think it's not smooth. So to any observation xj, the empirical distribution assigns a probability 1 over n. The contribution of xj to fn hat spreads its probability mass over this interval according to a uniform distribution. The ragged appearance of fn hat results from discontinuity. This is what I just draw. Discontinuities of the uniform density at its endpoints, right? An interval, just suddenly drop. This suggests a natural remedy in the construction of fn hat. But why? Replace the uniform density from xj minus h to xj plus h. Yeah, I should say that the density here is actually density is 1 over 2h, right? That's the density. Replace that density by some other smoother density, also centered at xj, with a scale factor h. And such a density can be written in this way. And this is actually what we call kernel estimator. And this is the kernel function. So coming back to this drawing I just have, right? So one thing to easily modify this, or I should say this is 1 over 2h. Sorry, I made it wrong. 1 over 2h. One thing to draw this is that you can still center a y, and probably you can have something like a Gaussian distribution, Gaussian density, right? The Gaussian is you can use h to specify the spread, but then every value will have some weight, and their weight changes as their distance to y changes, but it's not like 0 or something, right? It's not like 0 constant. So that is the intuition here, and this is the kernel function. Then with this change, you see, the estimator becomes this. That is, you are getting every value in your sample, xj, counted. J goes from 1 to n, and its weight entered this kernel density, right? Depending on how close xj is to y. The closer, the larger the value of k, then the larger the weight. That's pretty much it. So you see that I think that the whole development is very interesting because we first have this naive density estimator by plugin. We're trying to plug in the f using that approximation for the derivative, right? We're writing out the derivative as a ratio, difference divided by the length. Then we do plug in to replace f by fn hat. And then we realize that that is essentially corresponding to a uniform density in this kernel. Then we generalize that to be continuous because uniform is discrete, it's discontinuous. Uniform is discontinuous at its endpoint, right? The density suddenly drop down to 0 and we make that more continuous. So you see, this is the historical way of thinking about this density estimation problem. It's not coming out of nowhere. Okay, the scale prime factor h is called a bandwidth. You often see this in any density estimation like package, right? Or functions. You will have the density. You will need to specify the bandwidth because given the same sample, different bandwidth will give you different density estimates. It can look overly smooth or it can look very wiggly, right? If your bandwidth is too small, that's always the case. We shall assume throughout this section that k is a probability density. So that is non-negative and it satisfies this. It integrates to 1. And this is very, very important for other derivations we will see later. In addition, we shall restrict attention to densities k that are symmetric about 0. So it's a symmetric kernel. In generalizes 6.3. 6.3 is this one. We show that this naive density estimator is a density. It can integrate to 1. We also need to show that in this kernel version. Okay. Note that Fn is a probability density since it's negative, and we can show that it integrates to 1. So I'll just leave this for you to verify. Okay, let us now consider conditions under which the bias of this new kernel density estimator which generalizes the naive density estimator. We want to show under which conditions the bias tends to 0. Remember previously, when does that happen? When h goes down to 0. So basically, we want to ask this question. Is this enough? H goes to 0. And such conditions can be of two kinds. Restrictions on the kernel K. So now we have many choices for K. What kind of kernels are good? Because previously, we only have a uniform, right? And second, the true density of F. That is the thing we cannot control, ground truth. Since K is under our control, our choice, and F is unknown, conditions on K are preferable. We want to choose the conditions on K. Following 6.4.8, which is this, bias. This is what we had before. Bias for the naive density estimator is this. So therefore, we want H to be going down to 0, because then this will converge to that, okay? Following 6.4.8, we saw that when K is uniform density, as we specify H to depend on N, Hn go down to 0, the bias tends to 0 for any F that is continuous at Y. No further assumptions on F are needed. The corresponding fact is true for 6.4.13, this one. It's for the kernel density estimator. For this one, under very weak conditions on K, as is shown by the following theorem. Okay, let's look at this. Let F be any density that is continuous at Y, and let K be any kernel which is bounded kernel, so the maximum value is finite, and satisfies as you get away to either positive infinity or negative infinity, K times Y times KY is going down to 0. And this can be shown to satisfy for Gaussian. You know, Gaussian has a tail that is so light, right? Multiplying by large value is not enough, because this goes down to 0 much faster than Y increases. Okay, then the bias of this tend to 0. Or equivalently, we have this we have this consistency as H go down to 0. Essentially, the bias goes down to 0 as H go to 0. So again, this is just a condition we need to specify for the kernel. And we know this holds for sure for uniform, right? Okay. So that's it. Okay, so here, another thing, let me see. To prove this, in this book, they actually uses some smoothness assumption about F. So let's look at that. So what I just said for now regarding the unbiasedness can be proved if we add some conditions on F. So basically, we said F is 3 times differentiable with bounded third derivative in a neighborhood of Y, and let K be a kernel symmetry about 0, with this is finite, and this is finite, and this is finite. So these are all smoothness conditions. And also regarding its tail, basically tail probability. Then for any sequence satisfying this means Hn go down to 0. If they satisfy this, then the bias of this kernel density estimator takes this form. It's 1/2 times the bandwidth square times the second derivative of f at y times some tau square. So what is tau square? Is this one. So this is just a notation here. And plus something small o of hn squared. Okay, because this is hn squared, that means these terms are negligible given this term. In addition, hn satisfies this. That is, remember, n times hn go to infinity. With this satisfied, when then variance casts this form. So the first term is on the order of 1 over n times hn, and other terms are smaller than that. Okay, so what do you take from this thing? You see that the bandwidth hn has opposite effects on the bias and variance of the kernel density estimator. On the bias, you prefer to have a smaller bandwidth. That makes sense, right? Because a smaller bandwidth, it means that the data points you use to estimate the density are really close to y. You're not using data points far away from y to estimate the density because that will create bias, right? That's the intuition. But variance, if you have smaller bandwidth, you have larger variance. That also makes sense because if the bandwidth is too small, you have too few data points around y to support your estimation. So that's why there are opposite forces in these two things, and you want to balance the two. Right? So when you have this bias variance trade-off, we see it here, there must be some optimal, right? What is the optimal bandwidth? Okay, so skipping all these proof details, let's just focus on this term. Focus on these two terms. And we want to look at bias and variance jointly and do some optimization. That's just the thing. Okay, so I'm skipping all the detail, but I'm just saying that this is something very classical in our statistical estimation. Mean squared error equal to bias squared plus variance. I think you have seen it before, right? Somewhere in some other classes. So first of all, we know that as these two conditions hold simultaneously, mean square error will go down to 0. But between the bias and variance trade-off for a given n, how do I find the optimal hn? hn, how do I find it? So bias variance trade-off, where I'm using the formula we just got already. Okay, so this is the dominant term from the bias square. This is the dominant term from the variance. And this is a remainder. Compared to these two, they are smaller. All right, then treating this as an optimization problem, you want to solve for h to see what is the optimal h given n. So you write these two terms, you only keep the order of h. So in the first bias square term, h is h fourth, multiplied by something as a constant, I call that a. Second term, h enters as 1 over h times some constant, I call that b. Okay, but b actually depends on n. Just put it here. But here, I would just want to find the optimal h value that balances the two, because the first one increases with n, second one decreases with n, right? So they counteract each other. There must be an optimal n. So this is just a simple calculus problem. How do I find the h that minimizes this sum? And then we take the derivative. We call this g. We take derivative with respect to h, and we set the derivative to 0. And we solve that. So this is the h in this order. Now I put my a and b back. So this is a, this is b. Put it back. And here it is. Final result is this one. So putting that back, this is the optimal h. You see, it depends on f, depends on kernel. This is also tau square depends on kernel. This is f second derivative. But these are the things we fix basically. F is unknown, k is our choice. What we can change, sample size. So then this is the order of h. H should be in the order of n to the 1/5. Okay. And then putting everything back, you see, putting everything back, which is here, mean squared error. So now you choose h, say, this is your h, n to the negative 1/5. Putting this h back here, then you can get the rate for the mean square error instead of n, right? And you find that to be what? So 1/5 here times n here, you actually get order 1 over n to the 4/5. and this is the rate. And essentially, this is in this discussion part here, it says that this rate is slower than the typical rate of doing our like the central limit theorem thing, like the mean estimation thing, because in that case, the mean square error has a rate 1 over n. So density estimation is actually slower in this case. Yeah, that's pretty much it. I want to say that. So basically, we show that for this density estimation problem, we can use the bias variance trade-off to find a proper order for setting the bandwidth, which is this one. So you can know roughly, right? Even though these are the constants you don't know, but you know roughly how it should change with your sample size and what order. At least you know that. And that's just the mean squared error for fixed y. So because we're estimating fy. Now, if we want to say integrated estimation error, what do we mean? It's this one. So we're not just looking at one particular y, but we integrate over all possible y values this density can take. So that's another perspective. But still, it does not change our conclusion regarding the bandwidth choice, because we are still trying to do something similar to what we did. Let me try to find this part. Yeah, so we still get that result, even though we look at different criteria. So essentially, what we have talked about so far, we can stop here, is that we chose optimal bandwidth by the mean variance trade-off. But another question we can ask is, can we also use this to guide our choice of a kernel, right? Can we have an optimal kernel? And actually, there is, yeah. So we can continue from there next time. Yeah. So density estimation is something, as I said very early on, I think it's very useful in practice. Yeah, it's a lot of, because we do data exploration. Okay, so thank you, and then I'll see you next Monday. Yeah, thank you.